All right, today we're going to get into something that is fundamental to, well, basically everything you're using to watch this. We're talking about forward bias. It's the tiny on switch that makes our entire digital world go round.
So, think about it, it's one thing to have electricity, but it's another thing entirely to control it. You have to make sure it only goes where you want it to go when you want it to. You need traffic cops for electrons.
So the big question is, how do you actually build an electronic one-way street? You need a component that acts like a perfect little valve, one that lets current flow through easily in one direction, but slams the door shut if it tries to go the other way.
Well, this elegant little solution to our traffic problem is a device called the PN junction diode. For our purposes, you can just think of it as the electronic gatekeeper. It's the hero of our story today.
So what is a diode? At its heart, it's just two special types of materials sandwiched together. You've got a p-type, which has a bunch of positive charge carriers called holes, and an n-type, which has a surplus of negative electrons. And right where they meet, at that junction, something kind of magical happened.
Okay, so when the diode is just sitting there, doing nothing with no voltage on it, the electrons and holes right near that junction mix and cancel each other out. This creates what's called a depletion region. It's basically a barrier, a dead zone with no free charges that acts like a closed gate, stopping traffic cold.
All right, so we've got this closed gate. How do we open it? Well, we've got to give it a push in just the right way. And that push is what we call applying a forward bias. And this is what we mean by forward bias. It's actually super simple. You take a power source, connect the positive end to the P side of the diode, and the negative end to the N side. This external voltage directly fights against that natural barrier inside the diode. We're literally using an external force to muscle that gate open. And wow, this slide just shows it perfectly. Look on the left at image A. See how wide that depletion region is? That's our closed gate. Now check out what happens in image B when we apply that forward bias. The external voltage shoves the positive and negative charges toward the middle, and that barrier just shrinks down to almost nothing. The gate is swinging wide open.
Okay, so the gate is opening, but what's really going on down at the microscopic level? Let's zoom in and see what those charge carriers are actually doing to make the current flow.
You can think of that barrier as a steep hill that the charges have to climb to get across. At equilibrium, that hill is way too high. But when we apply a forward voltage, we're basically bulldozing that hill down, making it way, way easier for electrons on one side and holes on the other to just pour across the junction.
And this flow of charge happens in three basic steps. First up, we have injection. That's the voltage pushing the main charge carriers across the border into enemy territory. Next is diffusion. Once they're across, they're now the minority, and they start to spread out. And finally, recombination. They eventually find an opposite charge, they combine, and that completes the circuit, allowing a nice, continuous current to flow.
In this graph here, it's a perfect picture of what's happening. You can see the concentration of those extra carriers is super high right at the junction, and then it tapers off as they spread out and recombine. That movement, that spreading out, that is the current we're talking about.
Okay, here's the really cool part. Once we apply just enough voltage to get over that initial hump, the current doesn't just creep up, no, it explodes.
I mean, just look at this graph. This is the classic IV curve for a diode. For the first little bit of voltage, nothing happens, crickets. But then you hit this magic point and whoosh, the current just shoots straight up. A tiny little nudge in voltage causes this massive exponential rush of current. The floodgates are officially open. Now this might look like total chaos, right? This sudden explosion of current. But it's not. It's actually incredibly predictable. And it all follows one beautiful, precise law of physics.
And here it is, the Shockley diode equation. This is the secret recipe. This formula is what perfectly describes that insane exponential curve we just saw. It connects the current, ID, to the voltage, VD. It's the mathematical blueprint for how every diode works.
Okay, so we've got this tiny little electronic on switch. Big deal, right? Well, yeah, it's a huge deal. This simple idea is one of the foundational building blocks of pretty much all modern technology. Seriously, think about it. That charger you use for your phone, it's packed with forward bias diodes, turning AC wall power into the DC or battery needs. The screen you're looking at right now, it's lit up by LEDs, light-emitting diodes, which are just special diodes that glow when you forward bias them. And deep inside the processors of our computers, this exact on-off switching action is the basis for the logic that's doing billions of calculations every single second.
So it all comes back to this one simple, powerful idea. A diode is a one-way street for electricity. Its ability to let a ton of current flow forward while blocking it in reverse is what makes it absolutely essential. It's electronic traffic control in its purest form.
Which, of course, brings up a really obvious question. We've seen how forward bias is the on switch, but what happens if we flip the voltage around? What happens if we try to drive the wrong way down this electronic one-way street? Well, that's a whole other story, and we'll get into that next time.